Guys, I hope you're having a great evening and a great week. I will just quickly wait for you guys to, say hi. I hope you can see everything. This is the question that we'll be doing today. We'll be looking at the code over here. Can you see me properly? Can you hear me properly? Can you see both the code and the question properly? This is an interesting question, and not just for recursion but BST concepts also. So we are taking BST concept one level ahead. We are going to be talking about balanced BSTs today, and we'll understand how to convert a normal BST to a balanced BST. We'll understand what is balanced BST. So please confirm that you can hear, see me properly. You can, everything is fine. Then we can get started with the question. I am waiting over here, and as I said earlier also, you can let me know during the live if you have any doubt, and not just doubts. If you want me to pick up any particular question, we can do that as well. I love talking to you guys and connecting with you all, so you guys need to tell me what you are looking for and like that. Okay, so this is the question that we'll be doing today: normal BST to balanced BST. And see, there's a BST that is given to us. Now, what is a BST? It is basically a binary tree where there are all the nodes on the left value on the left are smaller and on the right are bigger, right? So this is the only thing for a BST, that okay, all the nodes on the left should be smaller, all the nodes on the right should be bigger. All the nodes, the left subtree and the right subtree, should also be BST themselves, but it doesn't talk about the height. So you can see over here that this is also a BST, even though height of this tree is a lot. Okay, so there are no right children, there are only left children. So the height of this BST becomes what? 4. 1, 2, 3, 4. There are 4 levels to it. Now, what does balanced BST mean? Balanced BST means that the height is as less as possible for the same number of nodes. So here also, see, if this is the BST that is given to us, we have to convert it into a balanced BST. Means here the height was 3. We have to make the height such that it is minimum possible. That, if we have to include all the 3 nodes, in the first level, obviously, there can be only one node, right? In the next level, there can be 2 nodes. In the next level, there can be what? 4 nodes, right? Like that. Since there are 3 nodes, the minimum height that is possible is what? 2. So here the 3 nodes are set up like this. Here there are 4 nodes. So if we want to keep the height minimum, here the minimum height is what? It is 3. There is 1 node at the top, then 2 nodes, then 1. So there are 3 ways of finishing this one, if you can see. So if we can put 3 as the root node, or we can put 2 as the root node. So there are more outputs possible. So basically we have to make any one balanced BST and we have to return. The balance means what? The height should be minimum. It doesn't say that okay, this should be the root or it should not be the root. Here 2 can also be the root, 3 can also be the root. The only thing is that the height should be as less as possible. Okay, so firstly, when do we say that the height is as less as possible? Say there are n nodes. Okay, so if there are, so let's say there are n nodes. When will the height be minimum? So we have to what? We have to minimize the height. How can we minimize the height? So that we make sure that the difference of the number of nodes is as less as possible on the left side and the right side. That means almost same number of nodes on the left side also and on the right side also. We have to make sure that there are almost same number of nodes on both the sides. So that is what we are going to do today. We have to make sure that the number of nodes is almost equal on both the sides. Now for that, I also have to make sure that the BST rules are true, that all the nodes on the left side are less than all the nodes on the right side. So to rearrange, what am I going to do is I'm going to first do the in order traversal. When I do an in order traversal of the BST, what happens that I have all the nodes in a sorted manner. Now I can take the middle one, make it root, and I will make sure that okay, now my tree is balanced. You understand? First, I'll take in order traversal. I'll have the sorted nodes. Then what will I do? I will make sure that it is balanced, that the height is minimum by dividing into half, making sure the middlemost element is the root itself. Don't worry if it's not clear. We are going to take examples. We are going to understand it properly. So if you have any doubts, you can ask me also. Okay, let's start looking at the code. And when we look at the code, it will be more clearer. So when we start, I am looking at the chat as well, guys. So if you have any questions, feel free to drop it in the chat. It will actually be easier for you to understand if you talk to me, if you can ask me any questions. Okay. So this is the tree that we are building. This is the root. So first check what do we have to do every time we solve a question, that if there is no root, basically if we are supplied with null, then what do we have to do? We have to return null itself, right? Because if we start referring the null value, then we are obviously going to have a crash. So we don't want that. Now I need to store all the nodes in a sorted manner. So I need to store them somewhere. So what am I going to do? I'm going to take a vector of nodes. So I'm going to take a vector of node pointers basically, and I'm going to call it what? Let me just call it nodes itself. Okay. Then what am I going to do? I'm going to store this in sorted manner. So let's call it in store in sorted manner. Okay. And what do I need to pass? I need to pass the root and I need to pass the nodes. Okay. See here, what is going to happen is I'm just going to store the addresses in the sorted manner, address to each node, but the left, right, I am not reassigning right now that, okay, my left node will be what, my right node will be what, that and all I'm not doing. So here I am just making the nodes in sorted way. So let's do that first. So I'm going to write this function. I don't need to return anything from this, right? I am just storing this in a sorted vector. So that is what I'm doing. So I am passing the root value and I am passing the vector, right? And I need to change this vector itself. So what am I going to do? I am just going to pass it by reference. So it's easier. Guys, why do we pass by reference? Why do we pass by value? Now you should be able to answer these questions. So I want you to tell me in the comments. Okay. So when we do in order traversal, what do? We first go to the left node, right? So we will check like this. So if root ka left is present, then what am I going to do? I'm going to call the same function, right? Because I'm doing what? I am doing in order. So first I'm going to go to the left node. So I'm going to go to the left node and I'm going to pass the same thing. And then I am going to deal with the present root that I have. In order, what do? Left, then the present one, and then the right, right? So left I have dealt with. For this one, what do I have to do? I have to basically push it, nodes dot push back. Basically in the vector, I am adding them in the in order way, right? So I'm going to push back this particular root. And after that, what am I going to do? I am going to deal with root ka right. In this, what am I doing? I am going to go like root and passing nodes, right? Okay, so here when I am dealing with the left one, I have to pass what? I have to pass root ka left. And here when I am dealing with the right one, what do I have to do? I have to deal with root ka right. Okay, now there are multiple ways of writing this and you should be able to tell it yourself. See, if we don't put any check over here and we always call, then in the starting I would have to put a check that if the root is null, then return from there itself and don't do anything. Okay, so multiple ways of writing the code. I can either put check over here, or instead of these two checks, I can put one check in the starting. If I don't put this check and if I put a check in the starting of the function, what is happening? I'm reducing the number of calls. I'm increasing the number of calls. But here I have reduced the number of calls, but I have increased the number of checks. So it's just different way of writing code. But I hope you're able to understand this. All I've done, I've gone to the left subtree. Then I have dealt with this particular node and then I have dealt with the right subtree. So this is in order traversal. Now, once we have done this, what do we have in this particular nodes? So basically in this vector, I have stored all the nodes in a sorted manner. Sorted how? Sorted according to their data. Okay. So I'm taking up questions. To retain the values in a vector, we are passing it as a reference. Good, Shivai. I really like how Shivai has been so regular and has been asking questions and answering as well. So thank you, Shivai, for showing up every day, and I hope others get inspired by you. Code Love is asking recursion. We are basically doing recursion in this also, but we are solving a BST question today. Okay. So now we have all the nodes sorted and we have stored them in a new vector. So now what do we need to do is, now we need to form the balance tree. So, and we will need that balance tree to be made, right? So we will need another function over here. So let's call it create balance tree. Okay, balanced BST. And what am I going to need in this? Firstly, I'm going to need the vector, right? So I'm going to pass the vector. I'm going to call it nodes itself over here. And I will need two values that I'm dealing with. Now, why am I passing these two values? See, we are going to be dividing our nodes into two halves. The middle element is going to be the root. The left part of the sorted vector is going to be the left subtree. The right part is going to be the right subtree. But we are going to reduce the index values. See, earlier my the L and H values will be 0 and n minus 1. But out of this, what will happen is, suppose this value n minus 1 is suppose 3. Okay. So what is the middle? Suppose it is 4, to make it easier to understand. So my middle value becomes what? 0, 1, 2, 3, 4. So my middle value becomes 2, right? So now my 2 will become root and my left subtree will be what? My left subtree will be 0 to 1 and my right subtree will be what? It will be basically 3 to 4, right? So this is how I'm dividing. So there is one small number and one bigger number. So basically one lower number and one higher number, which is telling that, okay, we have to deal with what range. So my range I am dividing into half, right? This is what we do in binary search. We are sort of dividing our bigger problem to a smaller sub problem, and that is why this is recursion, right? So what am I going to be doing over here? I have to first add my base condition. Basically, where am I going to stop my recursion? Where am I going to stop my, I'm going to terminate my balancing the BST. When is that going to happen? If you have watched the binary search series, then you should be able to tell this yourself. See, lower value should also be less than or equal to. When it is equal to, that means we are dealing with one node. When it is less, that means there are more than one nodes. But when it becomes greater, that means our node has been formed and we have to return. Okay. See, here we are creating a BST. So obviously we need to return also something. So what are we going to return? We are going to return node star. Now, I want you to tell me in the comments whether you are able to think of these things or not yourself. So I am returning node star, right? So I'm creating a new tree altogether. So basically there will be a root element, right? I have to return that. That is what I'm going to store over here, right? And that's what I'm going to return over here. So I need the root of the new tree that I'm forming, and that is why I'm returning it over here. Now what will be my middle element? First I have to find the middle value, okay? And we have discussed this in the binary search series. Why do we do L plus H minus L by 2? So that overflow doesn't happen. You can take big values of H and L and understand that, if the values of H and L become int max and int max, then if we do L plus H by 2, it will become 2 into int max. Whereas if we do H and L as int max, it is going to become int max minus int max, so it is going to become 0. So basically we are avoiding overflow by adding this. I have covered it in binary search series, and I've also made a separate short video on this. So if you have doubt over here, just go check it out. Now what is going to be my root? My root is going to be my middle element. So whatever was at this particular index in the vector is going to be my middle element, okay? And what is going to be the left subtree? That is going to be on the left part. So what am I going to do? I am going to call this, and I am going to pass what? Okay, I'm going to pass the same vector, but now I have to divide my bigger problem into smaller sub problem. L will remain same. The higher value will become mid minus 1. Why mid minus 1? Because we're including L and H. So L, mid has already gone to root. Now we have to go till mid minus 1. Similarly, we have to assign root ka right also. Right? See, earlier we had just stored the nodes in a sorted vector. We had not assigned the left and the right values. We have to assign them over here, and there will be some node value that will be returned, and that will point to the left and the right value. Now, see, when there is no node, basically we are returning null also, right? So initially there would be some left and right. We have to make sure that if it is a leaf node, then we assign it to null, okay? Otherwise it's not going to work. So we have to make sure that we assign the values as null also, otherwise they would be pointing to the previous left and the right children. So we have to make sure that we update that. So now my lower value is what? Mid plus 1, and the higher value remains same. So this is root ka right. After this, what is my root over here? We have to return that also, right? So this is dealing with the left subtree with the range L to mid minus 1. This is dealing with the right subtree with the range mid plus 1 to high, and we are returning the root over here. Okay, so now what am I going to do? I'm just checking the chat section again. Cannot see the whole code. Give me a second to just make sure that you can see the whole code. I hope you're able to see now, right? Okay. Scroll up, the code is not visible. Is it visible now, guys? Okay, my circle was blocking the code. I'm sorry, guys. I hope it is visible now, right? If there is any problem, let me just move this part over here. Okay, so I hope you are able to see now. Okay, cool. So now that we have assigned the left and the right values, what are we going to do? We are going to call the function. So I'm going to, this is where my sorted values were stored in the vector. So now I'm going to create the new node, the new root. So I'm going to call it new root. And what am I going to do? I'm going to call the function. And what are the values that I'm going to pass? The sorted vector that I had. The lower value was what? It will be 0. And what will the higher value? See, we have to include the highest most also. So what am I going to do? I'm going to do nodes ka size -1, right? So that is the highest value, n minus 1 basically. And I'm going to do what? I'm going to be returning new root. Now let's compile and see whether this works or not. I hope you are able to see the code now. Yeah, great. I hope you were able to understand the entire thing though. Right? Okay, so compilation has been successful. Let's submit and see. So we have passed all the test cases as well. Let me show you. Yeah, we have passed all the test cases. So I hope the question was clear. Let me just quickly revise it so that you don't have any doubts. So I'm also looking at the comments and if I have any doubts. And let us also discuss the time and the space complexity. Thank you for letting me know in the comments yesterday that we forgot to discuss that. I hope we don't forget that again. So what is the time complexity over here? First, we have stored all the values in a vector, right? So space complexity, we have used extra space. How many nodes are we storing? We are storing n nodes, right? So the space that we are taking is what? Order of n. Then we went through the entire tree once, first to fill the vector. So that took order of n. After that, we again went to the entire tree and we made a new tree. But we are visiting all the nodes once only. So it is order of n plus order of n, which actually becomes order of n itself. So the time complexity is also order of n and the space complexity is also order of n. And here it is given to us that n is between 1 and 200, and so that works. So what did we do over here? Basically, first we converted our entire tree into a vector and we stored the vector values in a sorted manner. And after that, we created a balanced tree. How did we do that? We took the middle element and made it root. And then we divided the left elements was the left subtree, the right elements were the right subtree. And we made sure that, height is as minimum as possible. But also, we have made sure that, BST, all the BST conditions are fulfilled. That means that the smaller values are on the left and the bigger values are on the right. I hope you understood the question properly. If you want me to pick up any one particular question, do let me know. I would really love to take any one particular question that you are having problem with. See you tomorrow. Tada, bye bye.